Hi everyone, my name is Andrei Kleshin. I'm a postdoc at the AI Institute in Dynamic Systems, which is an important distinction to make today. It's my pleasure to welcome everyone back to our seminar series after our break for the summer. It was quite extended, but now we're back for our regularly scheduled program. And today our speaker here is in person, so we're going to run the seminar in a hybrid format. We have a bunch of people in the room present, and we have a number of people online. So I will be handling any questions that come from online participants. So please just write into the chat if you have any questions to the speaker. Our speaker today is Professor Adarsh Krishnamurthy from Mechanical Engineering Department at Iowa State University, where he's also a member of fellow AI Institute in resilient agriculture. Yes, so this is, as we just figured out, the first time we are hosting someone from a different AI institute. So it's a great pleasure to have you here. And please, you can start. You should unmute and yes, have your video as well.
All right. Thanks, Andre. Thanks for
your video too.
Oh. Does it work?
Yeah.
Okay. All right. Good afternoon, everyone, or good morning, everyone. Today I'm going to talk a little bit about multi-scale modeling and simulations. And as I was telling Andre a little bit before, I'm trying to keep the AI aspects to a minimum, but there will be sort of AI in the background in all these things that we look at. So just to give you some basic definitions. So you must have heard this term digital twins a lot. So everyone has their own definition for digital twins. And this is one of the accepted definitions that we go for. So what we look at is basically a virtual simulation of the system, but not only that the system will have sort of bidirectional interaction with the environment, or the actual physical twin and the digital twin. So basically you need to have some sort of sensor data that is being accumulated on the physical system, and that feeds into the computational models, all the simulation models that's predicting the digital twin. So most cases, they sort of omit this interaction in the sense that there's only a simulation of the program, not really a digital twin. So that's one of the things that I wanted to emphasize. And the goal here is to sort of develop what are called as predictive models. So basically, they should be able to simulate multiple environmental conditions and then predict the system response as the environment is changing. So obviously, there are some fundamental challenges that you need to overcome for this. One of the things that I'm mainly focusing on is reconstructing the geometry. So basically, if you have a physical system that has some geometry, you need to replicate that in the digital system. You need to be able to generate the model systematically, so basically match parameters and things like that, and also basically replicating what is happening in the real world. And sort of inherent in all of these is that it needs to integrate disparate data. So, like for example, images, text data, or things like that, and then essentially integrate that to digital twin. So basically, sort of doing this manually is not a feasible process. So you need to have an automated way to do this in a digital twin. So one of the things that we focus on in the digital twin is, like I said, is one aspect is the simulation aspect. If you look at real world systems, they usually span multiple scales. So what I mean by multiple scales is that you could have something that is at a very, very small time scale or a length scale, going all the way to a large time scale or a length scale. And usually the way these models are solved is that you solve the micro scale problem, and then you go to the larger scale and so on. And then, but then what you need to happen is that there needs to be some feedback from the larger scale back to the smaller scales. And again, this is again going to be the most challenging aspect. I'll give you one example, since we are from AI Institute of resilient agriculture, we look at, say, plant modeling. You have to start from, say, the organ scale. So basically, these are like the tissue or the stems of the plants, how they would deform with some forces or things like that. Going all the way to the plant scale model, so how the plant itself will respond to environmental conditions, and going all the way to the field scale. So obviously, there are sort of complexities that are involved in each scale. But what is most interesting is that once you have this sort of multi-scale model, you have what is called as this emergence of complex behavior. And you sort of see this in sort of machine learning aspects as well. So there's this notion of this, why these large language models do really well is because they're so large. So there's this sort of this tipping point from which if the model becomes larger than a certain value, then you get interesting phenomena. So you have this emergence of complex behavior that happens. And then since I don't want to just focus on agriculture, I want to see how digital twins can be used in other aspects. So I just wanted to briefly introduce manufacturing, which is the other research I work on. So if you look at manufacturing, there's this notion of Industry 4.0, and sort of digital twin is one of the big aspects of this Industry 4.0 in manufacturing too, where you sort of integrate, say, 3D printing, big data, simulation, cloud, and cybersecurity to get a complete twin of the manufacturing system itself. So if you look at like all the things that happen during manufacturing, usually, again, this is focused on manufacturing, but you can sort of generalize it to any system. You start with the basics, which are usually like you build empirical models. Then if you are a little bit more advanced, you can think of them as model-based models, or like theoretical models that can be simple to solve. And then with the advancement of computational science, you had all these computational models where you use finite elements or these more complicated finite element simulations to do the same thing. But then with sort of the growth of machine learning and AI, you have the data-driven side where you can sort of use data and physics-aware machine learning to perform the same simulations. So if you want to do these simulations, what are the different ingredients that you need? So you need to have what are called as coupled simulations. So usually there is some sort of coupling happening in these simulations. So for example, if you're looking at flow simulations, there's coupling between the geometry and the actual flow that's happening. Similarly, if you're doing at structural mechanics, like for example, how a plant would sway in a wind, again, there is coupling between the solid of the plant and the fluid of the flow. So you have like what are called as fluid structure interaction simulations. Going further to manufacturing, you need to sort of couple with thermal systems and how the process is being performed in, say, additive manufacturing. And then if you're looking at more fundamental models like cell models, you need to couple them with sort of cell models to a continuum scale model. So these are some of the examples where you need to have some coupled systems. And I just wanted to show, I'll show some examples of coupled systems in this talk a little bit. So like I said, again, I wanted to show what are the different ingredients that go into, say, a digital twin. I wanted to emphasize on 3 different aspects that I want to talk about today. First, like I said, I look at geometry reconstruction. Then if you have reconstructed geometry, then how can you use the geometry to do some analysis? And then finally, I'll end with some manufacturing applications at the end. So one of the early problems that we looked at IRA, or the AI Institute for Resilient Agriculture, is we want to create a digital twin of a plant itself. And one of the things that you want to recreate there is the geometry of the plant. So why is reconstructing the geometry of the plant so difficult? The main reason is that the topology of the plant is complex in the sense that you have very thin structures that are connected together, which if you're not using the correct methodology to capture the data, you might miss it. So you might end up with sort of discontinuous or or separate components of the geometry itself. They're also flexible structures. So for example, if you're taking images, there are usually wind or some other aspects that might blow the plans around. So it gets difficult to reconstruct the geometry. And if you look at sort of the basics of geometry, there are two kinds of representations that you can think of. So, so if you say you have data, the most raw kind of data that you can have is point cloud. So basically, a point in space with XYZ coordinates. You can then do what is called an explicit reconstruction. So basically, if you're using splines or any kind of objects representation, that is called as an explicit reconstruction. Or you can use an implicit function, which is defined all over the domain space, and use that to extract out the geometry in some sense. So the most common explicit representation you might all be familiar with is triangular mesh. So here, each triangle represents a part of the surface. And again, you have different representation that represents the triangle. And in the case of implicit representations, the most common you might be familiar with is called as distance field. So basically, at any point in the space, you find the distance to the closest point on the boundary. And that gives you a field which you can extract out like sort of isocontours from that to get the geometry itself. So if you want to look at distance fields into more detail, they're really interesting because it's a scalar field, and they there are two kinds of distance fields that are usually used. One is called as a signed distance field. Another one is called as unsigned. The advantage of the signed one is that if you have an object which is closed, then you can have the sign represent whether the point is inside the boundary or outside the boundary. And this is particularly useful later when we are doing simulations, which I'll talk about in a bit. And the other aspect of the signed distance field is that they satisfy this iconal equation. So this is a partial differential equation in space. So at any given point of space, the gradient of the signed distance field always adds up to 1. So and then the components of the gradient of the signed distance field in the 3 directions gives you the normal to the object when the signed distance field is 0. So for example, at this point, if I take the gradient, it will point at the normal direction. So so we wanted to use this sort of neural or signed distance field representation for representing the plants. So how do we go about doing that is we use a terrestrial laser scanner, which is basically, it's there on your phone. So like iPhone Pro has a LiDAR scanner here. So it can get you the coordinates of this the plant at different coordinates. And then what we do is we use what is called a neural implicit representation. So the difference between a regular representation and neural representation is nothing but you just train a single neural network that takes in as a query point, and then what it outputs is the signed distance field that is associated with that query point. So what you have to do is that if you're given a new point cloud geometry, you have to retrain this this neural network for that particular point cloud geometry. So once you have a trained network, then you can use that network to query all the locations for the signed distance field. And not only that, you can extract out the isocontour that corresponds to the 0 distance value, and that will give you the surface of the object that you are interested in. So, and this is the only slide I have in terms of math and loss functions. So if you want to train a neural network to solve for the signed distance field, you take advantage of the fact that the signed distance field satisfies the iconal equation. So you can sort of put that in the loss function. So this is where it becomes physics aware in some sense. So the first term essentially says that the iconal equation is satisfied. And then the second term that you do is that you have a bunch of points on the surface of the object that you're interested in. So you can set, since you know that the sign distance field is 0 there, you can add that term of the to the loss term. And not only that, you can also get the normal. In some situations, you can predict the normal from the sign distance field or from the point cloud itself. So you can take the normal and add that as another term for the loss. But having just these terms is not enough, because you don't usually get a unique solution for this. For example, you can get a 0 everywhere, which is a trivial solution, which will satisfy all of these, which will not be useful. So what you then need to do is add this a regularization term, which is the interesting part. This is what is called an off-surface penalty. So what you do is you take some random points everywhere on the domain and say that those values should not be 0. So that's, you penalize the values that are non-zero there. And then in order to improve this sampling, you also sample what are called as k nearest neighbors. So for each data point that you have, you sample a bunch of points around those data points, and again set those values to be non-zero. And then you tune what has been interesting is that you have to tune these parameters, and people have looked at different ways in which you can tune these, and different tuning gives you better results as you see. So we sort of used these and tried different methods for point cloud reconstruction. So we just took a simple ground truth geometry, and these are sort of what are known as conventional methods. We don't use any neural methods, and these are sort of the neural approaches. And again, I'm not going into the details of all of these methods, but what we found was that SIREN, where SIREN stands for sinusoidal reconstruction network. So essentially, the activation functions in these networks are sine functions rather than regular ReLU or any of those activation functions. And that seems to produce the best result, at least in our limited example. And that was just visual comparison, but you can also do a numerical comparison. So the way you compute how well your reconstruction is using these two metrics. CD stands for chamfer distance. Basically, given a point cloud, it computes the closest point on the surface and takes that distance, and then it averages this distance over the whole set of points that you have. The other extreme is what is called the Hausdorff distance, which is the max of the min distance between two point clouds. So you can sort of see that SIREN produced the sort of the reasonable accuracy, or reduced accuracy. But not only that, the other thing that you need to worry about is the training time. So since you have to train a neural network for each of these objects, we found that SIREN produced the best, or the best results with the fastest training time. And these are some other examples of non-ground truth objects that using SIREN reconstructed. So that was just basic neural reconstruction using for sign distance fields. But if you're all familiar with the graphics literature, there's been this new approach called as NURFs. So NURFs stand for neural radiance fields, and it's the same idea as the sign distance fields, but instead of producing the neural network to use it to produce the distance value, you use it to produce the color value for a given direction. So I'll talk about that in a set. So, oops, I think I missed that slide. But maybe I'll explain it this way. So the way the sign distance field works, or nerves work, sorry, is that you give a ray direction, and then you also provide a point along the ray direction, which you use for the query. And what the neural network does is it predicts the color of that particular ray. Or in a simpler sense, I can talk to you more later in more detail. But essentially, what you then do is, say I have this view, I reconstruct this view from the nerve, and then I also have the same reconstructed view from actual image, actual data, or virtual data using graphics principles, and then you compute the loss on the image space, and then that's what is used to perform the training. So once you have trained this, then you can essentially reconstruct the whole 3D geometry of the whole scene. So so this is how a standard pipeline with NERF would look like. So you just collect a bunch of images. One of the difficult aspects of NERFs is this part, where what you need to do is then estimate the pose of the camera with respect to the image. Once you do that, then you train the NERF with this information. And once the NERF is trained, you can extract the geometry out. So so I'll show you a simple example. So this is a different views of the plant that has been captured. And then there is this method called COLMAP, which is basically structure from motion, which estimates the pose of the different views. So you see that these are the different views from which these images were taken. And this is of order of about 20 or 30 in this case. We can reconstruct the whole 3D geometry of the whole scene from just this limited data. And not only that, we can then use traditional marching cubes to extract out the plant geometry itself. Yeah.
How does this work with the reflections?
Yes. So
because it basically sees that there are objects, I guess, deep under the floor.
Yes, exactly. So that's where it gets really, really interesting, is that basically what the NERF is doing is it's doing a virtual ray tracing, and it somehow is able to pick up the reflected rays because that they were present in the original image data. And that's where it gets really, really interesting. So and you are right, because I think this year's SIGGRAPH, there was a paper which was optimized just for reflection, so it can produce reflections really well. And not only that, like what's even more interesting is that now you have this reconstruction, you can sort of play with the reconstructed data in virtual reality. So this is one of my students looking at a virtual plant, which has been reconstructed using NERF. And basically, you can sort of go in and look at different aspects of the plant. And where this gets very interesting is some of our agricultural collaborators, they're really interested in this because they don't then have to go to the field in, say, 80, 90-degree weather and check out. What they do is they have to do these inspections every day to see whether a plant is resilient to some like drought or heat or things like that. Now we can just send a robot which will collect this data. We can do a 3D reconstruction, and then the plant breeder can see it in virtual world and essentially make the same decisions that they would make in real life. So, like I said, some of the recent work that has been done on NERFs are on like large-scale reconstruction. There's something called block NERFs. So the 360-degree scene I told you, that was done using what is called MIPNERF 360. And then there's also been a lot of work done on speeding up the training time. So so previously NERFs used to take almost like 8 to 10 hours for a scene. Whereas instant NGP, it takes about 10-15 minutes, and you can get the same resolution. And yeah, so there's a lot of work being done right now on NERFs, and that's something that I find super cool and interesting. So just to sort of summarize the first part of the geometry part of the work, so we sort of looked at different implicit neural representations for plant geometry reconstruction and also nerves. And we find that, again, there's a lot of new exciting things that's been happening in this field, and it's always ripe for new work to be done. So that was sort of the first part. So now say you have a point cloud geometry. What can you do with it? So this is where we sort of looked at another way to analyze data, or essentially perform CFD simulations or FSA simulations. So essentially take the point cloud data and see whether, without actually reconstructing and meshing and doing all sorts of things, whether we can simulate CFD simulations directly with the point cloud data. So just to give you a background, if you're doing CFD simulations, this is what happens. So you take a CAD model, you then do what is called a boundary fitted mesh. So essentially the CAD model has to conform to the boundary of the object, because you're interested in the fluid flow outside the object mostly. And then you perform the CFD simulation. So this is what it looks like. So if you have like a tractor or any vehicle that's going in outside, then you need to sort of mesh the outside region, and you need to make sure that the mesh is fine around the boundary of the object to capture all the important physics that happens there. More often than not, these kinds of things happen. So you have like meshing issues. So, and you have like sharp corners, you have like pinching, and basically these can take about weeks or months if you have a complicated shape like a tractor or a car or things like that. And that's one of the pain points for industry as well as other folks. And they usually say that it was interesting because I met with some people who said, oh, it takes 6 months. And everybody said it takes 6 months. And I was curious why exactly it was 6 months. And the reason was that they try for 6 months and then they just give up and take whatever they did for 6 months and use it for safety simulations. So, so the approach we wanted to take was this idea of what is called immersive geometric analysis. So basically, the idea here is that you take a CAD model, and then you directly immerse it in what is called a background mesh. So what you see here is that the mesh exists both outside and inside, and then sort of you apply some fictitious boundary conditions on this geometry surfaces so that you can the flow will actually feel the effect of the geometry. So so then you don't have to worry about this sort of geometry cleanup or anything. You take the geometry, put that into the background mesh, and then perform simulations. And we wanted to take this to the extreme. So now, if you don't even have this geometry but just have a point cloud, so what do you do with that case? So so you need two important things that needs to happen when you do the simulations. One, you need to integrate over the surface of the object. The second one is you need to perform what is called an inside-outside test. So you need to figure out for any node on the mesh, if that node is outside the object or inside the object. So if you're looking at point cloud, so you don't really have a surface. So that's where things get interesting. So basically, point cloud are not what are called as watertight. So basically, imagine if you pour water, they will essentially leak out everywhere. So, sorry, let me. Sorry. So the other thing that you need to think of is that now if I have a point here, how do you determine whether it's inside or outside the object? So we looked at, so we sort of systematically solved these two issues. So one thing that we need to solve is that we need to estimate the normals of the surface given a point cloud. And so for doing that, essentially what you do is you find the closest point or k nearest neighbors for the singular point on the point cloud, and you construct what is called as a Voronoi surface of that particular region. And then you use that Voronoi surface to estimate the normal, as well as the area that is associated with that particular point in the point cloud. So by doing that, let's skip that. So by doing that, essentially what you can do is you don't have to worry about the distribution of the points. So you could have a randomly distributed set of points in the point cloud, but you can still do surface integration and get the accurate surface area because you are using this Voronoi surface tessellation. So that takes care of the surface integration. For doing the inside-outside test, that's where, again, we have to be a little bit more creative. So the standard way you do inside-outside test is that if you take a point, you just shoot a ray in any random direction. If the ray intersects the boundary of the object an odd number of times, that means that the point is inside. If the ray intersects the boundary an even number of times, that means it's outside. So that's how standard inside-outside test is done with objects. But then if you are having gaps or if you have point cloud, then this test becomes very difficult because obviously, for example, here, this point is actually inside, but then it sort of ended up, the ray ended up going through the gap in the object. So it'll be wrongly classified. So to deal with that, a couple of folks at University of Toronto, they came up with this idea of what are called as generalized winding numbers. So winding number is a measure. It measures how much time you, if you are at a query point, how many times you go around the query point as you go along the boundary. If the winding number is positive, usually that means that you are inside the object. And if the winding number, if you're outside the object, it'll be 0, basically. And what these folks at Toronto did was they extended this winding number calculations to any discrete objects like point cloud, for example. So the way they did that is they converted that into a line integral, or essentially integral over the object boundary. And then you can sort of approximate that with solid angles and essentially get the same idea. So if you do that, this is what you get. So this is an example of a generalized winding number. So what happens here is that you have an object, but there is an extra boundary here. What happens in this case is that the winding number here inside is 1, but outside is all 0. And then this region has a winding number which is greater than 1. But then if you have a cutoff at 1, you can still get the correct boundary of the object. The same thing you can do for a bunch of points on the circle. So you essentially have a region, a small region around the boundary where the winding number is between 0 to 1. But then that is a clear definition between 0 and 1 inside. So essentially, you can sort of have a cutoff at, say, 0.5, and you can get an approximate boundary of the whole object. Yes?
You just mentioned that this is supposed to be translation invariant, or does it only hold approximately? Like here in your cross example, it varies within.
Yes. Yes, exactly. So it is translation invariant.
Or it's like the sinus.
That sinus translation, and which is what we are interested in, or rather, whether it's 0 or 1 in some sense.
Okay.
Yeah. So then we can perform the same inside-outside test with these point cloud information, and then we can do fluid simulation. So again, these are some benchmark examples that we did. So take a sphere made up of point cloud, run fluid simulations, and the results accurately matched experimental as well as other simulation data. And then we looked at an even more complicated example of a wheel loader. And these are some of the results for the flow simulations. So just to reiterate, so if you have a point cloud data, we have sort of found a way to perform fluid flow simulations with directly on the point cloud data. And obviously, some of the future work that we were looking at is like, can we use sort of machine learning to improve this? So one thing we looked at was use like a neural network for the winding number calculations, because this is again a physics aware machine learning, because you have integral equations. We can use a neural network to do that. We have a publication just still under review about that. And other thing is that for estimating the normal directions, again, we can use neural networks or other approaches to improve the normal estimation. All right, how am I doing it now? Okay, I can quickly go through the manufacturing application. So the other application that I wanted to talk about was for additive manufacturing. So again, we have a separate effort focusing on trying to build a real-time digital twin for additive manufacturing. So again, like I said, the idea here is that you have a machine tool, which is a additive manufacturing, a 3D printer. You use some sensors to get some information from the 3D printer, and then we can essentially get a real-time digital twin. One of the advantage then, once you have a digital twin, is that you can sort of actuate based on what you see. Say, for example, there's some defect or some aspect that's being wrong, you can sort of correct for it. So that's sort of the grand vision. Obviously, we are not close to it right now. So one of the first things that we looked at was to do these simulations in real time. So for what we wanted to do in that case is that we take a CAD model, we essentially voxelize the CAD model. Basically, voxels are like small pixels in 3D. And then what we can do is we can create the G code, which is basically the instructions that are given to the 3D printer. We can also take the same G code and create what we call as a virtual simulation of the same process. And then while we are simulating this, we also wanted to incorporate thermal effects, because that's one of the important things that you need to take care of. So once you do that, then you can sort of compare the actual part with the simulated part and see if there are any differences that can happen. So we are at the early stages of doing this thermal simulations. So basically, you're solving just simple Poisson's equations. So like I said, we take the G code, we do the voxel printing, which is basically printing voxel by voxel. One of the difficulties for doing this is that if you are having a voxel grid of, say, 256 cube, you are sort of, the compute cost is like super expensive if you are doing voxel by voxel. So what we do is we use an octree-based framework. So octree is nothing but you sort of combine regions where there is no information, where the boundary is not there, to get a larger voxel in some sense. And sort of this reduces the simulation costs by a lot. And then essentially we can then perform this voxel by voxel printing, and then we can get simulation results. So again, I'm skipping over a lot of details here. I'll be happy to talk with you later if you're interested. But essentially, we can do this sort of simulations in real time. Not yet, but we are doing almost 2x the time. So basically, if it takes 10 minutes to print, our simulation takes 20 minutes. So that's the goal right now, to sort of make them real time. So what you see here is that each voxel is being printed, and that's very hot because it's extruded material. And then after it's being printed, it sort of cools down slowly over time. And this is the octree structure that you see here. So as more and more voxels get printed, sort of they combine together to get a bigger voxel. And we tried this for more complicated geometries. So this is an example of a bunny and the Moai statue. And as you can see here, sort of interesting effects can be seen because of this. So one of the things that's very interesting is that sort of we want to make this resolution independent. so that you get the same results even if you use a sparse resolution or a coarse resolution or fine resolution. And this is the more interesting aspect. So obviously, when you're 3D printing something, you usually don't fill it 100%. So you have like less infill. So for in this example, this region is not filled fully. This is a completely filled bunny, and this is a completely sparse bunny. And what you can see here is that in the completely filled bunny, the temperature or the ear or the face of the bunny cools much faster than in this case, because here the heat dissipation through conduction at the bottom is not that that high. So that's something that's interesting. So sort of we incorporated this idea with a real 3D printer. So we took a 3D printer, incorporated what are called as depth cameras. So these are stereo depth cameras that give you 3D point cloud information. And then wanted to see whether we can monitor this in real time. So just a brief video showing the same process. So we incorporated 3 different cameras, so we can essentially get information from all those 3 as the 3D printer is printing. So this is obviously sped up, I think 20 times. And as the object is printed, our goal is then, like, while it's being printing, do the thermal simulations. And not only that, we can do the 3D reconstruction of the object from the depth cameras. So basically, this is one view, this is the second view, and this is the third view. You can sort of combine them together to get a 3D point cloud of the whole object. And not only that, you can project that to the actual CAD model and see where there is high deviations between the simulated model and the reconstructed model. Yeah.
No, just when to take one each.
Oh,
Yes.
So again, sort of end with some interesting future work in terms of this, since again, we are part of the AI Institute. What's been really interesting is this whole LLMs and conversational AI tools. And one way conversational AI can help in manufacturing is that they can provide sort of immediate response at the assembly line. So for example, if an assembly worker is assembling something and he or she is interested in, say, he has part A and he or she is interested in what goes with that. So he or she can immediately ask the conversational AI things like, how does part A interface with part B? And things like, what's the dimension of this part, and things like that. But one of the key roadblocks for doing this is that, as you all might know, they're prone to hallucinations. They can make up data. So that needs to be some sort of metric for correctness to figure out whatever the LLM is responding back is actually correct in some sense, or there's some confidence associated with the response. And there's been some recent work done on conversational AI for design. So this is like using a text prompt to generate a 3D world image. And there have been like interesting advancements here. The other thing that the AI tool can help is with process planning. So for example, if you have a G code that works with, say, one flavor of machine tool, you can ask the LLM to produce the other, matching flavor in other flavors. So these are some of the things that the LLM can help really well. And in fact, you can sort of go through the whole manufacturing pipeline and see how the conversation can happen at each stage, and have a complete sort of like LLM enhanced manufacturing pipeline in some sense. So sort of summarizing that, so sort of we looked at some digital twin framework for manufacturing, and also looked at like how conversational AI can help with manufacturing itself. One thing I didn't touch upon is that another thing that we wanted to focus on is like cyber attack detection. So if you have a machine tool, I don't know if you're following the news, but there was a recent article where all the 3D printers by a company started switching on by themselves due to, this wasn't an attack, but this was like a bug in the programming. But you can imagine if someone wants to attack your 3D printer, it's very, very easy. Like the security is very, very little. And especially if you're making some critical component, you don't know whether the attack will change the component, that you end up with a lot of wastages and things like that. So this is where like a real-time process monitoring or digital twin can help mitigate that attack, or at least point out that something bad is happening. So with that, I wanted to also acknowledge my students, without whom none of these would have happened, and the funding sources, and then I'll be happy to take questions.
Okay, there was a quick question in the chat about sharing the video. All of the recording of the seminar would be posted on our AI Institute website. So yeah, now we're happy to take questions. So anyone in person here can ask questions directly. Anyone online, please write into the chat and I will voice them out.
Awesome.
Oh,
yeah.
That was immersive geometric analysis. I didn't quite understand why that helps solve issues such as sharp corners and other meshing issues.
Oh, because so in traditional CAD, you have to mesh the object. So basically, the object here has to be meshed. Like the boundary outside of the object, or the 3D space has to be meshed. Whereas here, in immersive geometric analysis, like it's sort of the mesh sort of intersects, or the object boundary intersects the background mesh. So you can sort of independently mesh the background. And to take it to another extreme, you don't need to have unstructured mesh for the background. You can have a structured mesh, like just have like an octree or a voxel mesh, and then just have the complicated shape of the object overlaid on it. So that's how you don't have to worry about. Given said that, there are some issues when you have what are called sliver cells. Like if you have like a background mesh cut very small region by the foreground objects. And there are some approaches to mitigate those, and that's where the research is in this immersed approaches. So, yeah.
For the heat transport on the 3D printing stuff, it's obviously very complicated with the airflow,
Yeah.
heterogeneous,
Yeah.
and everything. So is that do you believe that they will actually make good digital twins that can do that anytime soon?
I think that, like I said, I think we are sort of close. Like I said, we are almost like 2x to 3x slower. And if we make some assumptions, we can speed that up a little bit. Yeah, I would say maybe a year or two away to between. And obviously, I didn't talk about the advancements in like GPU computing and things like that, which would help in some sense. So
It would be great because
yeah,
obviously they fail all the time.
Yeah, exactly.
So I think you spoke a lot about simulations where the fluid is flowing outside the boundary.
Yeah.
But have you like tried, how would you do this for something that's not flow to a pipe?
Right.
You want to analyze the flow to a pipe inside. So have you tried?
Yeah. So in terms of the methodology, there is nothing different. Like all you have to do is like, because the mesh also exists inside. So all you do is like change the domain that you're interested in. In fact, like if you're not careful here, we find that the flow sort of leaks inside, and you'll see interesting results if that happens. So yeah. Yeah.
Software which is open source or available for use on this thing as of now.
Nothing I know of. So all of these are custom, our own code base. And another main distinction is we use finite element simulations. So traditional CFD uses finite volumes. And if you are interested in finite volume, there is OpenFOAM, which is supposed to be really good in terms of flow simulations. Yeah, thanks. Any other questions?
Nothing in the chat.
Okay.
Anyone in the chat, please, you have another couple minutes. So I guess I can ask about this, like the plan geometry scanning. Like how tractable would be if plans start moving? Like if you want to know, you know, how much does this thing oscillate in?
Yeah. So that's a really good question. So one thing that we looked at is I didn't talk about this here, but sort of like a probabilistic reconstruction rather than a discrete reconstruction. So what we wanted to do is if you're reconstructing, like say, a voxelized plan geometry, for each voxel, you can associate like a probability that it is part of the plant or not just like a binary 0 or 1 classification. And we tried doing that for like using approach called as voxel carving. So basically here what happens is that you look at the object from, say, one view. I can carve out all the voxels that are outside this object, and then I look at it from here, and then I carve this voxels out and things like that. And if you have sufficient number of views around, you can sort of get the shape of the object. And we sort of converted that to a probabilistic approach where you don't carve out completely, but you just carve out thinking of like, what is the fraction of this view that's being seen? And that helps in slight movement of the geometry. And we find that the regions where the probability is very high, you can for sure say that's part of the geometry of the plant. And regions where the probability is like very, very low, then you probably have to do something to see whether it's due to the movement of the plant or things like that. So that's something. And to be honest, doing sort of uncertainty quantification with nerves is very, very new. So there was a recent paper on UQ for nerve like a few weeks back, actually, I think. So and yeah, so that's again an active area of research.
We have a question from chat coming in from Francis Zhu. Have you considered using other simulation methods like soil contact models or more surface-based sims instead of particulate-based sims?
Very good question. Me personally have not worked on those, but our institute, we are developing something called as an ag gym. So basically this is like especially our collaborators at CMU, they're developing articulating robots, which essentially sort of insert sensors onto the plants. And for them, we need a model of like the contact of the arm of the robot with the plant geometry itself. And one of the things that we are sort of in the early stage of looking into is those kind of contact simulations and things like that will aid with the robot for essentially for RL reinforcement learning.
Cool. Yeah, thanks. Francis is happy. Anyone else from here, from online? No, then I think on this we can wrap up. Thanks everyone for coming, and please be on the lookout for announcements of our next seminars with dates and speakers and all that. And we'll see you all around. Thank you.